should be, can you see the slides?
Yes, perfect.
Beautiful.
Very good. Let me know when I can start.
Okay, shall we start? It's a great pleasure to have Daniele Bianchi from Queen Mary University of London. He's going to talk about dynamic variable selection in high dimension predicted regression. The floor is yours, Daniele.
Thanks a lot for having me, and thanks all of you for being here. What I'm presenting today is still a little bit of not a work in progress, because we've been working on this paper since quite a while, but as usual, there are lots of moving pieces. So I'd really love to have your feedback, comments, and suggestions on how we can improve the paper. So feel free to interrupt me anytime if something is not clear. It's a joint work with Mauro Bernardi and Nicolas. Nicolas is currently doing a postdoc at Pompeu Fabra, and Mauro is a colleague in Italy at the University of Padua. As the title says, I'm going to talk about dynamic variable selection. So the problem that we are interested in is how we can select variables in a what we call high dimensional regression space, and how we can select variable dynamically, meaning that you might have variables that comes in and out of the regression, and you don't know a priori when they comes in and when they go out. So here's the outline of the presentation. So I want to give you a little bit of an overview of why we're interested in this problem and how people often approach this issue. And then I want to talk about the model and how we approach the problem of inference. It's going to be a Bayesian framework, and in particular, a variational-based framework, so what we normally call approximate inference. And I'm going to walk you through briefly through what variational base is and how we actually set up the algorithm and some of the algorithmic properties. And then I'm going to touch upon a simulation study. Probably we'll spend some time on the simulation part. Usually I spend too much time, but I think it's worth to highlight some of the properties of in particular, the inference scheme. And so I'm going to spend some time on the simulation, and then we have an empirical application, which is primarily just to showcase the methodology. And we're going to look at the problem of forecasting inflation in the US, looking at different inflation measures and a large panel of macroeconomic variables, roughly slightly more than 200 macro variables in a quarterly frequency for different horizons. So, the problem that we have is a regression with time varying parameters. So nothing particularly exciting in the underlying, let's say, framework. Think about a dynamic regression where your parameters, the regression coefficients varies over time. You may or may not have stochastic volatility. The way you typically model time variation in the beta could be around a walk. That's typically the case in applied macro. Or perhaps if you need stationarity, it's going to be in layer one, and that typically the case, for instance, in some of the empirical finance paper. Now, typically, the way people think about variable selection in a time-varying parameter space is unconditional, meaning that if you take out a variable, you take out the variable for the full trajectory. So if you say that some of the x's don't matter, the rationale is that never matters. So for the full trajectory or training sample, so to speak, the variable is always excluded. Now, what we argue, though, is that perhaps it could be interesting to look at a situation where your beta could be at times significant, at times maybe not, like in this very simple example, and maybe become significant again and maybe not by the end of the sample. So that obviously raises some issues from an inference perspective. But that's basically what we have in mind. Now, there are a couple of things that make the whole inference problem more complex. The set of predictors could be large, so your set of x's could be potentially very large, approaching to t, so approaching to the number of observations. The signals could be heterogeneous, meaning that the strength of the sum of the x's could be larger than some others. So you might have the dynamics of these betas could change dramatically across the corresponding axes. Maybe for some betas, for some axes, the corresponding betas is always in the model. For some others, is never in the model. For some others, is in the model only for a short-lived period, and so on and so forth. So you may have lots of heterogeneity in the signals that is brought by the axes. Now, the reason why the second, let's say, issues, and is one of the primary reasons why we're interested in this problem, is if you include the relevant variables in a state space framework, that becomes even more problematic than an unconditional, let's say, static regression, because you no longer have capital P predictors, but you have capital P times T parameters, because at each time T, you get a parameter vector. And so if the problem of having irrelevant variables becomes particularly relevant in a state space framework where you have dynamics in the betas. And then ultimately, this is a bit more an intuitive point, you don't know a priori the dynamics of the beta. So you don't know a priori when a given predictor matters and when it does not. So there is obviously lots of uncertainty there. So if you put together all of these issues, so the idea that a predictor could be relevant at times, maybe not at others, the fact that this has potentially relevant consequences for the state space dimension, and there is lots of uncertainty on these dynamics in the first place. I guess one could realize that this is not necessarily a trivial issue. Now, nevertheless, we are obviously not the first one looking at this issue. I'm classifying now what I would call different groups of models or different type of approaches. By no means this is an exhaustive list, but just to give you the idea on how different people so far thought about this problem of variable selection in a dynamic system. The first, let's say, group of models, what I would call naive approach here, is basically a simple rolling windows, whereby you have whatever static variable selection approach you can think of. If you're a Bayesian, that could be a spike and slab. But if you are a frequentist, that could be a lasso or an elastic net, could be many things. By the idea that you impose some non-parametric dynamics via rolling window. So you keep your 60 months of data, and then you move the rolling window on, and then at each time you do some variable selection, and you assume that within that window, the variables are never relevant or they're always relevant. I call it naive because you don't necessarily impose any particular dynamics on the parameters. All is driven by the rolling window, and that depends on the length of the rolling window, or maybe if you prefer an expanding window versus a rolling window and such. There is what I call a second class of models, or a second, let's say, class of approaches, which are being designed for smaller dimensional cases. There is this nice paper by Raftery, it's published in Technometrics in 2010, and introduced this idea of dynamic model averaging. The idea is that you try all of the possible combinations of your regressors. So you get 2 to the power of p, and p is the number of predictors, so 2 to the power of p possible combinations, and then you're going to look at basically what is the marginal likelihood of each of the possible models. You're going to aggregate for each regressor, and then you're going to get some sort of probability of inclusion of each of the predictors. So it's really like a model selection, but what you would call in a closed set, meaning that you try all of the possible combinations in your model set. Then there is this nice paper by Nakajima and West, is a JBES published in 2013, and they introduced this latent threshold model. And the idea is very simple, and to some extent we borrow a little bit from that idea. The idea is that you have a, let's call a nuance parameter or a latent parameter that basically is going to switch on and off a latent beta. So you have a beta that could be, let's say, a random walk, and then you have an hyperparameter. Then when the beta across that hyperparameter becomes active, and when it's below becomes inactive. So they call it threshold model because the nuance parameter define the threshold above which the corresponding beta gets activated, and the opposite. And then more in a Bayesian context, there is this framework by Carlin Griffin, is a Generic Econometrics 2014. They introduced this normal gamma autoregressive process. And a similar idea has been introduced by Beaton Fruishnatter, it's a Generic Econometrics 2019, and by Koval and Cotters, is a Journal of the Royal Statistical Society 2019. And basically what they do dynamic shrinkage, which is not variable selection, but you get basically the idea is that you have a time varying beta, and then you're gonna inflate or deflate the variance of the beta such that it becomes basically a flat process or a highly volatile one. It's called dynamic shrinkage because it's a time varying parameter setting. And then if you're a frequentist, what I classify as smaller dimensional frameworks, and I'm gonna clarify later on why the fused lasso is a small dimensional method, you get indeed this diffuse lasso that goes back from Tip-Shirani in 25. So I call those a smaller dimensional for the reason that, and I'm going to show you the simulations later on, they all work very well, and they all, wonderful models. But the problem is that as soon as you go beyond 20 predictors, they just break up, they just don't work, or you don't get the results in a finite computational time. So all nice and smooth, but the problem is dimensionality there. Now, more recently, there is a class of methods, and I'm actually missing apologies, I'm missing a reference here. You get the dynamic spike and slab by Coop and Korobilis, is an international economic review, and then there is a Bayesian analysis by McCallin and Rochkova in 2021, and there is a paper by Edibert Lopez and co-authors that should be cited in the paper, but I missed the reference here in the slides, with whereby they all propose a dynamic spike and slab. So you have a mixture distribution a priori, and there is dynamic in the way basically you sample the beta from a Dirac at 0, or you sample the beta from a Gaussian, right? Now, all of this framework work relatively reasonably well in a high dimensional setting. We're going to compare specifically with Coop and Korobilis because it's a variational base like ours, and so it's like the natural benchmark. And we're going to compare also by Rochkov and McCallin because it's a frequentist approach. It's based on an EM algorithm and is actually very fast. So what we do in this paper instead, we basically built upon this huge body of literature, and I'm missing a lot actually here. So this is, as I said, by no means an exhaustive list, and there are lots of other people probably in the audience as well that work on this issue. And I apologize if I'm not talk about their work, but the literature is fairly large. I'm basically simplifying a bit. So what we do in this paper, we build upon this literature, and we propose a slightly different version of what has been proposed so far, which is a so-called Bernoulli-Gaussian regression, and in fact, a dynamic Bernoulli-Gaussian regression. So Bernoulli-Gaussian with a varying parameter. And I would say the main novelty here is not necessarily the design of the model, which is not particularly complicated, but the inference part, which has some advantages that I'm going to clarify later on with respect to MCMC. And this methodology is variational based, so variational inference. If I have to give you in a nutshell the main results, or let's say the main value proposition of the paper, is that variational inference is just as accurate as MCMC, and I'm going to show you that in simulation, comparing directly with the MCMC. But it's much faster, so it's scalable in higher dimension, while instead MCMC is not. So MCMC is clearly a bottleneck for a variety of reasons, but there are ceteris paribus. So for exactly the same models, if you implement MCMC, you just can't estimate the same model if you go beyond 30, 40 predictors, right? So there is clearly a computational bottleneck. I have to be careful here. I'm not saying that MCMC is not a good, approach to estimate this type of model. All I'm saying here is that there is some clear computational bottleneck that prevents you to scale up in high dimension, and variational base allows you to get over that bottleneck. That's basically the message here. So as I said, so the problem is variable selection in time-varying parameters. There's a variety of different approaches, from the static rolling window to the dynamic small scale, dynamic large scale, and all of those have been, they have pros and cons. They all work one way or the other. We build upon this literature by proposing a slightly different model with what I call a little bit of a radically different way to estimate those models. So what I'm going to do now, I'm going to lay out the modeling framework. So let's say the main features and characteristics of the model. And then I'm going to talk about the inference. I'm not going to go too much into the details of the variational, but I want to give you the intuition of what is variational in the first place, for those who are not familiar with it. And then I want to kind of try to link with MCMC, because there is actually a tight link between variational inference and MCMC, at least conceptually. So the model is a Bernoulli Gaussian. So the idea is that it's a steady space. The observation equation is a regular regression. So you get your dependent variable, YT, which is a scalar. So it's not a multivariate time series framework, it's a univariate time series framework. You get your scalar as a target variable, could be anything. In our case, it's going to be inflation, but could be stock returns, for instance, or could be many other things. And then you get a set of predictors X's, P, which is the set of predictors, could be basically as large as you want. And then the beta has some dynamic. And I'm adding here stochastic volatility because in the applied macro literature, people like to think about stochastic volatility in inflation. But if you don't necessarily agree with stochastic volatility, in the paper we also have the framework with homoscedasticity, so constant volatility. Now, how about the dynamics of the betas? The way we think about the dynamics of the betas here, and here is the Bernoulli Gaussian.
Daniele,
yes, please.
Can I ask, why are you using some sort of leading indicator model? Because your regressions are not in the same time interval, this time that your independent variable. Why is that?
Because we like to call this predictive regressions. So we normally lagged by one time observations, but the framework is general. I mean, I'm presenting here in a way that is consistent with the the narrative of a predictive regression, basically a lag variable of X, how correlates with futures values of the Y's. But if you don't like it and you want to talk about contemporaneous regression, everything goes through. So it's really just the labeling here is the literature that I'm appealing to that talk about predictive regressions. And normally the way these are laid out is YT and XT minus 1 or XT and YT plus 1.
Okay.
Not sure if that answers your question satisfactorily.
Yeah, but it's a leading indicator model, so, but you don't have problems of exogeneity and all of that in your regressor. So
no. I mean, I'm not getting to the debate if there is endogeneity between the X's and the Y's. So it's a purely predictive regression framework. So I'm not interested in any type of structural analysis here. So yeah.
Okay.
So regarding the dynamics of the betas, so it's a compounding process, and I guess now clarifies a little bit why we call it Bernoulli Gaussian. So it is conditionally on an indicator gamma that can take value 0, 1. That's a dynamic variable indicator. Conditionally on that indicator is a Gaussian model. So you get a time varying coefficient that I call B, and that I'm going to clarify what the dynamics of B is later on. And then you have this compounding process between gamma and B. Gamma tells you if a predictor is significant or not, or put differently, if it is active or not. And then if it's active, the dynamics comes from the B, and the B is going to be around the walk, as I'm going to show you in the next slide. Now, before showing you the pieces, so how the dynamics of the gamma and the B looks like, I just want to basically spoil what we are really after. So what I'm showing you here is a snapshot of some of the results that we have. And this pertains to the 1 quarter ahead GDP deflator, so one type of inflation measures. And I'm showing you here the surviving predictors, or the predictors that becomes relevant at least once for one observation in the sample. And this is basically what we are after. So the end game of our framework is to tell you, as you see here in the bottom panel, to give you an indicator when a variable is relevant, and that's the gamma. And when a variable is relevant, to tell you what kind of dynamic that variable has. And that's the top panels here. And this is basically the dynamics of the betas, which is the compounded between the B and the gamma. So, I just want to clarify or flesh out a couple of properties here. For instance, if you look at this is the industrial production final goods, or intermediaries. What our model is able to capture very short-lived signals. So you see, you get these spikes around COVID, and that's, I'm not sure, I'm not a macroeconomist by training, so I'm not sure how much I can justify this. But this basically tells you that the industrial production, or the pressure from the production side was particularly relevant around that 2 quarters. Or, I guess I don't have to convince you that the lag matters for inflation because it's highly persistent, but perhaps don't always matter, as these results show you. That's the lag. Or, perhaps is kind of intuitive that there is an inverse relationship between the 5-year yield, that's this column here, the 5-year yield, and the inflation rate. Or, as I showed here in the last panel, this is an inverse relationship between unemployment and inflation. That's basically the Phillips curve. And the interesting thing here is this is just short-term unemployment, not necessarily long-term unemployment. By no means here I'm trying to sell the framework as a structural model that can tell you, how macroeconomic shocks can explain inflation moving forward. That's not what we are after. All I'm saying here is that we want to have a framework that retrospectively can tell me when a macroeconomic variable had some predictive power, or at least correlate positively or negatively with inflation over the sample period. So it's basically the end game for us. And then, from now on, I'm going to clarify what, the features of the model, how we make inference, and the forecasting exercise. So hopefully convince you by the end that there is, in fact, some value when it comes to forecasting, auto-sample forecasting, in capturing this sort of heterogeneous dynamics in the parameters. Now, going back to the features of the model, as I said, the betas is this interplay between gamma, the indicator, and the B, which is a latent parameter. And the latent parameter is basically a random walk. So this B is a random walk, so nothing new in that sense. The reason why we picked a random walk as a dynamic is because you can specify the random walk as a so-called Gaussian macro random field, which is nothing but a Gaussian process whereby you have a tightly parameterized covariance structure. I'm showing you here this Q, which is the covariance structure of the B in the case of a random walk. If you don't like the random walk, you can have a Gaussian macro random field for an AR1, for an AR2, for an AR3. The only thing that changes is the off diagonal. You have more and more off diagonal, the more lags you do have. As usual, for this type of models, the reason why we picked a random walk is because makes everything faster computationally and simpler computationally. So the only parameter you have to specify really, or the only real prior you have to specify is this eta j square. And I'm going to talk about the priors later on. So this is the B, the stochastic volatility, same logic. The log stochastic volatility is a random walk, and the reason why it's a random walk is, again, because we can specify everything as a Gaussian macro random field, and in particular for the stochastic volatility, this is going to be key for the variational inference because, some computational trick that we can apply. Now, as far as the indicator is concerned, we don't model the indicator directly. We model the indicator conditionally on an auxiliary variable that we call omega here. So gamma given omega is a Bernoulli with some input, which is the inverse of a logit. And so this omega is again a random walk. And again, a random walk is picked because of the Gaussian-Markov random field representation, so for computational convenience. Now, it's not only computational convenience, but the reality is that if you integrate out or if you marginalize gamma with respect to omega, then you end up having a distribution whereby the persistence of gamma is directly inherited by omega. And so omega is not just an auxiliary parameter, but defines how much persistent is the omega or how much persistent is the probability that gamma has value 1 or vis-a-vis value 0. So as I write here in the slides, the serial dependence of omega is a direct function of the serial dependence of gamma, sorry, is a direct function of the auxiliary parameter omega. Now, I mentioned the priors, and as usual, as usually in a Bayesian context, you have to be careful because the priors matters, in particular if the likelihood is not particularly informative. So as far as the new parameters and eta j, so as far as the this is the variance on the B, and nu is the variance on the, let me go back here, nu is the variance of the latent volatility. As far as those two parameters are concerned, we resort to the literature and we basically take a very flat prior. Now, a little bit more extra care needs to be taken for the psi j square. And I'm highlighting here in red. And now, if you allow me, I just want to spend a couple of words on this prior because it's very relevant. So for the psi j, which is the variance of the latent omega, we need to give some specific recipe. So we need to give you a number, basically, in how you set up the scale and shape parameters. So if you allow me, I want to spend a couple of slides to do a little bit of comparative statics in how you set up the shape and scale parameters of the inverse gamma that defines the prior for psi. So basically what we do in the paper, we look at 3 scenarios. We look at what we call scenario A, whereby we let the shape parameter constant and we let the scale parameters grow very large. So A is constant, B plus infinite, very large number. And if you set up the prior in this way, then what you end up having is a situation like these 3 panels. The left panel is the correlation matrix for the omega, or the variational correlation matrix of the omega. The panel in the middle is the trajectory of the omega that comes up from the estimate. And the panel on the right is the trajectory of the gamma and the true gammas, which is these red lines here. So it is a 0 for half of the sample and is 1 for the remaining half of the sample. So by setting A constant and B very large, you end up having a process for gamma that is very volatile. So you get the gamma that goes all over the place, so completely miss out the true value of gamma. And the reason is because the omega is very volatile. The persistence or the autocorrelation here becomes relatively small. So you get an omega that goes all over the place. And as such, the gamma goes all over the place. That's scenario A. So we kind of exclude to have a situation where A is constant and B is large. Now, how about the opposite? B constant and A very large, or the scale parameter being constant and the shape parameter being very large. Well, you get the opposite. You get a situation where you have a super high correlation structure in the omega, which makes the omega flat, basically. You see here the scale on the y-axis. And as a result, the gamma is basically very low moving or low frequency movement and doesn't really go either to 0 or to 1. It basically gives you this indefinite trajectory, which is not necessarily a good thing. So scenario B, we also exclude setting the scale parameter constant and letting the shape parameter be very large. Now, scenario C is instead what we ultimately refer to our recipe, which is any value of YAB is good as far as the ratio between the two is a constant number. And the reason being is we experimented in simulation, and basically what we saw is that if the ratio between A and B being constant, you end up having a moderate level of correlation in the variational density for omega, which basically leads to a decent performance when it comes to the omega and as such the dynamics of the gammas. So all of this to basically try to give a little bit of structure in how we should set psi. And what we do in the paper, we suggest two values for the shape parameter being equal to 2 and the scale parameter being equal to 5. We also experiment with different values of the scale parameters, but the results don't change much. As far as I said, as far as the ratio between A and B is constant, the algorithm behave reasonably well. So apologies for this detour on talking about the priors, but this is something that I'm personally particularly attached to, because you know usually when you work with these methodologies of the common concern is, okay, how about the impact of the prior on the estimates? And we do basically as good as we could in trying to address those type of concerns. So I mentioned at the very beginning there is a variational inference framework. So what I'm going to do in the next couple of slides, I want to talk a little bit about variational inference, and also try to make the connection with MCMC basically. So what is variational Bayes? The idea of variational Bayes is to minimize the Kullback-Leibler distance, or the divergence between, I keep it general for now, what I call variational density here, so Q or theta, and the true posterior density, so P theta given Y. Now, the reason why variational Bayes is often applied could be either because you don't observe the posterior density, so you can't derive the posterior density, or maybe you do, but it's just too computationally costly to draw from the posterior density or to set up your MCMC for whatever reasons, for high nonlinearities, you need lots of metropolis hastings, you need lots of things that makes the computation very heavy. So in our case, it's actually the latter. So it's not that we can't observe the posterior density. We could. In fact, we derive the MCMC equivalent of the variational Bayes, but it's just too costly, or is too costly for us, at least. So what does it mean minimizing this Kullback-Leibler divergence? There is this nice paper by Orworth and Wan, I think is an American statistician, the journal, and goes back to 2010. And what they say minimizing the KL divergence basically corresponds to maximize the so-called effective lower bound, which is this object here. And the effective lower bound is a function of things you could, in principle, observe, because it's a function of the joint likelihood, so the likelihood of the data and the parameter. And as far as you have a model, in principle, you can characterize the likelihood. And the variational density, so this Q or theta. So finding out the optimal theta means basically maximizing this effective lower bound. Now, I understand that this looks like a little bit of esoteric. So what I'm going to do next, I just want to give a little bit of intuition of why basically maximizing the effective lower bound is sort of the equivalent of maximizing the marginal likelihood, or at least get something close to it. So why maximizing the elbow, and why variational inference focus on that? So let's consider a general density, so Q of theta, so general density function in a given parameter space. By that arbitrary density function and leveraging the Bayes rule, you could rewrite the log of the likelihood or the log of the marginal likelihood as a function of the joint likelihood of the data, the variational density Q theta, and your posterior. Now, this is an integral, so you can, in principle, you can break it in two pieces. So one piece is the KL divergence. So is a distance between, in probability space, is the distance between Q and P. So the variational density and the posterior. And the other object is the what I call effective lower bound before. So de facto, you get equality if the variational density is exactly the same as the posterior, but in that case, you don't need variational Bayes in the first place. But if not, de facto, maximizing the log marginal likelihood means minimizing this divergence, or put differently, maximizing this part here that is left, which is the effective lower bound. So the bottom line really of variational Bayes is that you want to approximate something that is very complicated or it's very costly to sample from, which is the posterior, by setting up the variational, which is in principle simpler or at least less computationally costly. And the reason is working with the effective lower bound is more tractable than working with the marginal likelihood. So it's all about complexity versus simplicity in a computational sense, really. But conceptually, is basically you're just trying to maximize the likelihood in some way, or at least something that gets as close as possible to the likelihood in some way. Now, where tractability comes from, and there is several ways in which you can approach tractability in variational Bayes, but one of the most common one, at least in an econometric context, is the so-called mean field variational Bayes. And the idea is that if you believe me that finding this density q theta is kind of akin to maximizing the likelihood, and for tractability reasons, then the way you can get tractability is partitioning that density q theta. So basically partitioning the joint variational density. By partitioning, I mean factorizing. So if you think about a regression setting, a static one, you can think about, instead of having the density of betas and sigma together, you just assume independence, and you model the density of betas and sigma separately. So if you do that in a mean field variational Bayes, and as I said, there are different ways in which you can approach variational inference. Mean field is probably one of the most popular. So it's a choice that you make. It's a estimation choice. But if you do that, then the same Ormerod than one paper, they tell you that you can actually calculate the optimal variational density starting from the full conditional. So if you can derive your posterior, as we could, because in principle there is nothing that can prevent us to derive the full conditional of all of the parameters, then it's just a different way to working with the conditional, the full conditional distribution, which means that you just have to take the expectations of the log of the full conditional, and then you have to iterate in a coordinate ascent algorithmic fashion. You have to iterate across all of the densities. So it's no longer a simulation base. So it's no longer, you don't draw from the full conditionals and with the hope that at some point you get convergence. Here is a stochastic optimization. So you get the density, and then you get the expectations, and then you iterate in a coordinate ascent fashion. It's kind of close to the EM conceptually. You get an expectation step, and then you have to maximize. The expectation is what comes out from the mean field, and the optimization is the coordinate ascent. I'm not going to show you the algorithm here; it's too boring. But in the paper, we have obviously all of the propositions and the full derivations of the algorithmic steps. I'm going to show you in a few slides the pseudo algorithm, just to give you the idea of the whole package. But this is as good as it gets for this presentation. There are a couple of ingredients. So as I said, you have to factorize the variational density, which is, this factorization basically allows you to have the equivalent of something like an EM, so an expectation maximization. But then you have to decide what is the form of the factorization. So the factorization of the density for us has some ingredients, in particular, 2 ingredients. So this is all of the parameters that we have and all of the factorizations that we need. We need to assume independence in some sense. So when it comes to the 2 ingredients, one ingredient is about the stochastic volatility, so what I call here Q of H. And the idea here is that we're going to assume multivariate Gaussianity, which is not outrageous for log volatility, but gives us lots of computational power in the sense that things can become simpler to compute. So we're going to assume that the log volatility is multivariate Gaussian. Multivariate because we look at the full trajectory of log volatility, and so is a multivariate Gaussian. The second assumption that we have, remember that before I talked about gamma given omega, so the indicator given the auxiliary parameter omega. And here, basically, what we're assuming that instead of modeling the conditional distribution, gamma given omega, we have to factorize. So we can no longer assume a conditional dependence. So we have to assume independence. And to model this relationship between gamma and omega, we choose a so-called polygamma representation, which allows you basically to have sort of an equivalent representation of the gamma given omega that I showed you before. Now, all of this is technical details, and the details are in the paper. I'm not going to spend too much time. If you want to talk about it later on, I'm happy to answer any question. So we have this factorization. We decide, a priori to assume that log volatility is conditionally Gaussian, and we decide to break up the conditional dependence between gamma and omega by using this polygamma representation, which buys you basically independence. The third ingredient, which is something that we introduced recently, is how we could think about correlated predictors. Now, for those of you who work with variable selection, correlated predictor is the key thing, or is one of the things that referees usually point out, and for good reasons. Because if you have highly correlated predictors and you do variable selection, then it's not even clear, what does mean, how the correlation affect the oracle properties of your sparse estimator, for instance, and and so on and so forth. So now we have an issue here in the sense that factorization buys you the efficiency. So factorization allows you to do the coordinate ascent. So factorization allows you to get the computational speed that you need to scale up dimensions. But on the other hand, perfect factorizations for the beta means complete independence across the axes. So each of the beta trajectories is treated as a separate process, which means axes are uncorrelated to each other, which is not necessarily realistic. On the other side of the spectrum, if you assume that the betas are all correlated, so the x's are all correlated, then you go back to square one, because you could have like this big dimensional matrix that you need to invert for the betas, and so you no longer have the computational gain. So we borrow this idea, which is not necessarily their idea, but is an idea that they implement, by Mogliani and Simoni. It's a recent paper, as a working paper, is an archive, whereby we assume a priori some group structure. So the idea is that we don't do factorization for P predictors, assuming independence. We don't treat everything as a single block. We treat things as in blocks, basically. And that gives us a little bit of a trade-off. So we can still get computational efficiency, and we still get reasonable correlated features, correlated x's in empirical analysis. I understand it's a caveat, and I fully appreciate that ideally you want to treat, very general correlation structures, but at least for this iteration of the paper is as good as we could do. Now I'm not sure how much time do I have left. Is it 15 minutes? Is it?
Yes, about 15 minutes, yes.
15 minutes. So I want to quickly digress, skimming through two features of the algorithmic part without going to the details. I just want to give you the idea. So we got two issues. One issue is the gamma. So the indicators are entirely data-driven. And if you have noisy data, you can get the gammas that goes over the place. And here I'm showing you an example whereby you have a very short-lived gamma. So gamma gets, above 0.5 and then below 0.5 the next observation. And if it's fundamental, is okay, but if it's noise, is not, because that actually translates in an erratic dynamic for the beta, which could be, could have consequences in the forecasting sense. So what we do, we impose a smoothing process on the estimates of gamma, and basically we use a wavelet, but you can use these splines if you don't like the wavelet. There are plenty of details in the paper, but basically there is what we do, we try to smooth out the dynamics of the gamma so that we can, instead of these erratic dynamics, we can get something that is smoother. The second digression that I want to make is related to inference and to irrelevant variables. So one of the issues that we observed was that if you have lots of noise, so you have 200 predictors, but only 10 matters, and 190 is just pure noise. Now, this in principle shouldn't matter much for the consistency of your estimate, but for the efficiency, it does. I mean, it's like OLS with irrelevant variables. The betas is still asymptotically valid, but the variance might be inflated. Now, this obviously has consequences when you do variable selection, in particular, given the let's say the iterative structure of the coordinate ascent. So what we do, we kind of embed in the algorithm what I call here online screening. And the rationale is very simple. Just focus on the left panel. What I'm showing you here is on the x-axis, the iteration of the coordinate ascent. On the y-axis is time, and the color gives you the significant, and gamma is the indicator. So what this panel here on the left tells you that we show in simulation that our algorithm quickly converge if the variable never matters for the full trajectory, quickly converge to impose sparsity on the full trajectory. And if you believe in the results, what you could do, you can discard variables in batches so that, for instance, after 10 iterations, you have 5 variables that don't matter. You take those 5 variables, you take out from the regression, and then you restart the algorithm again, so that you shrink, you online screen the X's, basically. And that buys you efficiency. And in particular, what we notice algorithmically, at least, is that we can get more accurate so-called sparsity-inducing properties of the algorithmic part. Now, this is, details, but I think is worth to mention. So here's the algorithm. The details are in the paper. So I'm going to briefly talk about the simulation study, and then hopefully, if I have time, the empirical application. So regarding the simulation, we do 2 exercises. One exercise is what everyone asks, which is how you guys do compared to MCMC. Does it really worth it? Is it really worth it to bother you with variational inference when you have indeed the MCMC? And the second exercise that we do is how does compare against other existing methods. So I start from the second, and then I go back to the MCMC later on. So in the first simulation exercise, we generate a data generating process with 50, 100, or 200 predictors, 100 replicates, and then we have different dynamics for the betas. We have what I call here a dynamic intercept. So you have a beta that is always included. You have a dynamic sparsity. So you have 6 different betas that could take different dynamics. So maybe 2 switches, maybe 3 switches, maybe 1 short-lived switches, different dynamics in terms of their significance over time. And then everything else is noise. So here goes back to the point that I mentioned before. You might have different levels of noise in your data set, which means you might have the ratio between significant and insignificant predictors could change. And that ultimately, in principle, could affect inference. And in this particular setting, we're going to get basically here with 50 predictors, 42 are noise, with 100, 92 are noise, with 200, 192 are noise. So the ratio between noise and signals or noisy predictor vis-a-vis significant predictors could change across simulation settings. We consider different versions of our estimation algorithm. We have the what I call BGS, which is, let's say, the main guy here, is the model with smoothing, but then we also try without smoothing. We take out the heteroscedasticity, so stochastic volatility, and we also try the model fixing different values of the shape parameters for psi, as alluded before in the comparative statics. We're going to look at different benchmark methods. We could do more. We could, expand to other benchmarks, but you kind of believe that this is sort of representative enough. We have a static spike and slot, as implemented by Rochkov and George. The lasso, the fused lasso, the dynamic model averaging of Raftery, the dynamic spike and slab of Coop and Korobilis, and Rochkov and McCulling, and static horseshoe of Corvai and co-authors, and the dynamic shrinkage of Kova and co-authors. As I said, this is representative, by no means is an exhaustive list. We just believe that captures most of the methodologies you normally could use. Now, in terms of metric for the simulation, we're going to focus on one metric in particular, which is the F1 score. And the reason is what we're ultimately interested in is not necessarily in the mean squared error of the beta. So if you accurately estimate the betas or not, what we're ultimately interested in is in the variable selection. So it's the gammas. If a variable is deemed significant in the data generating process, can we exactly capture that or not? And that ultimately is a classification problem. So you end up having true positive, true negative, false negatives, and all that. And if you look at the classification literature, what they normally use for as a performance metric is the F1 score, which is the ratio between true positives and true positive, and false negatives. This is also nice because it goes from 0 to 1, and 1 means perfect identification, 0 means bad identification. So in the remaining 2-3 slides, or sorry, in the next 2-3 slides, I'm going to show you a bunch of box charts whereby we have different models, different classes of models, and all of this is for the correlated predictors. I should remember by heart how we impose correlation in the simulation, but I don't. So I refer on the paper, for you to check. So what I'm showing you here, you see 5 panels, and hopefully you see the dashed gray line vertical. So you see the first panel is all of our Bernoulli-Gaussian specifications. These blue ones is the dynamic spike and slab of Rochkov and McCallin. The green ones is dynamic variable selection of Coop and Korobilis. These ones are the small scale approaches, so the fused lasso, dynamic shrinkage process, and the likes. And everything that is gray and white is the rolling window approach. So I'm looking here at 10 predictors, and which means that I can still run the fused lasso, the dynamic moving model averaging, and the dynamic shrinkage process. But you can see already that in particular, the rolling window doesn't necessarily capture anything that comes close to the true dynamics of the betas, while instead our Bernoulli Gaussian performs decently. I also want to highlight here that you see here BG MCMC because it's the exact MCMC counterpart of the variational base. If you remember before, I mentioned that in the iteration of the coordinate ascent basically comes up from the full conditional. And if you have the full conditional, you can do your Gibbs. And so that's what we do for comparison. Now, with 10 predictors, you can still do the MCMC, but if you go to even 50 predictors, you just can't do MCMC anymore. It's too computational costly. So I want to highlight here that you don't have the MCMC even with 50 predictors. You don't have the fused lasso, the dynamic model averaging, and others. And our framework kind of outperform the others as well. And if you enlarge the dimensions, we don't get, even with our framework, we can claim to have a perfect identification, but they are certainly better than others. Series computational time in log minutes. You see that this is the MCMC in yellow. So after 20, just isn't feasible, and even below 20 is an order of magnitude slower than variational base. And if you look at this trajectory, which is our framework, turns out to be the most efficient, even compared to other variational base, like Coop and Korobilis, which is the green line here. So I mentioned before the second simulation exercise, which is the direct comparison with MCMC. So what we do here, we have variational base and MCMC, the same model, so counterpart, and we borrow a metric that goes back from to a paper by Wand and co-authors, which is basically, we look at what is the distance between the density that is implied by MCMC, which is in red, here is labeled in red, and the density that is implied by variational base, which is labeled in blue. 100% means that there is 100% overlap in the density, 0% means that there is 0% overlapping in the densities. I focus here on the joint. Joint means that we take into account the beta as a single block, and we could do that because the dimensions are smaller, so we could do that comparison. And you see that we get reasonable close to 100% overlap with MCMC. Now, the reason why we don't get perfect overlap is incidentally because the variational base is more efficient than MCMC, at least for this model. By more efficient, I mean that when you have a switch, if you see on the 2 zooms here, when you have a switch from significant to non-significant, in MCMC, you can still sample from the distribution where the beta is 0. While in our setting, being stochastic optimization or EM, if you like, it directly switches to 0. So it's tightly around 0. If you see the density, it's not that it does not approximate MCMC well. It's just that MCMC is more thick-tailed, so it's actually less efficient than variational Bayes. This is for our model. I'm not claiming that MCMC is less efficient in general. There are lots of caveats here, lots of flags, but in principle, we observe that variational Bayes and MCMC overlap decently. So is as accurate as MCMC. We could claim that. Now, in the remaining 2 minutes or so, I want to quickly go through the empirical application, which is inflation predictability. So we do the exact exercises of Köppen-Korobilis and Rochkov and McCullin. We look at 1, 2, 4, and 8 steps ahead or quarters ahead. We look at 4 measures of inflation. We have 229 predictors from the new data set by McCracken and G, and we also include 2 lags of the response. We have a sample period that is basically, T is actually close to P here. We look at as forecasting benchmark the unobserved component model of Stock and Watson, which is basically local level, and the time varying parameter AR1. And I tell you, in advance that these are very tough benchmarks to beat. So we're not going to beat those benchmarks for the most part, but we beat everything else. So we beat all of the variable selection methods that have been analyzed in this work. We look at recursive forecast, so 10 years burn-in, and then expanding window. So here is the point forecast accuracy, mean squared error. And we're going to look at the benchmark. So time varying intercept is the local level of Stock and Watson, AR2, time varying parameter AR2. We have static selection rolling. We look at a PCA, which is not selection, but is a data dimensionality strategy anyway. We look at the horseshoe, we look at the static spike and slab, and we look at the recent prior implemented by Giannone Lenza Primiceri in the econometrica last year. And then we look at also the dynamic selection. These 4 columns are our framework. The last 3 columns is Rochkov, McCullin, and Köppen-Korobilis. 4 horizons, 4 measures. Average means the average performance across inflation measures. Dark red means bad, light white means good, and long story short, static rolling does reasonably bad, and dynamic selection does reasonably worse than our framework, which is this part here of the table, which in turn does not necessarily better than the time varying intercept of Stock and Watson, which is sort of expected for us, and it's a tough benchmark to beat at the end. But if you want to use macro variables, our framework does better than the others. We also look at density forecast. The time varying intercept doesn't do well anymore. The reason is is very good in predicting the conditional mean, is very good in predicting the point forecast. But when it comes to it, because it's very tight around the mean, if you get an observation that is slightly far away from the mean, then completely screws up. So the time varying intercept for density forecast is no longer that good. On the other hand, the time varying parameter A2 is indeed a good benchmark. But if you look at this part of the table compared to static selection or dynamic variable selection, we do reasonably better as well. So I think I'm, for the first time in my life, I'm on time, which is good. So what we do in this paper is we look at dynamic variable selection in what I call reasonably large dimensional setting. We show that is accurate, or at least as accurate than MCMC, and is scalable, certainly more scalable than MCMC. It's competitive against other approaches. There are nuances, but it's competitive. And then what we're currently thinking at the moment is developments, in particular, generalized linear models. So in principle, in a Bayesian context, you can think about a quantile regression as a conditionally Gaussian if you use an asymmetric Laplace, for instance, approximation. So you can actually think about our framework in a quantile sense or for count data. Now, it requires a little bit of modification, but in principle, you could do that. Some development that we're thinking of that is, requires perhaps more thinking and more work is to look at irregular time points. So not anymore in a well-behaved time series setting. And something that we're currently experimenting is networks, because in principle, you can think about constructing a directed acyclical graph based on the time varying variable selection. So selecting connections in a regression context it could be used eventually for network. I mean, this is way above my head. It's not something that we're planning to do. Came up from a conversation that we had with Mike West some time ago, but I just leave it there. And for those of you who are interested in playing around with the framework, Nicolas, who is the brain behind the coding here, has the R package on his website. Thanks a lot for your attention.
Thank you, Daniele. Any questions? Diogo has a question for you.
Hi, my question is about outliers or large outliers. If you have the gamma jumping from 0 to 1 in these points, for example, when you show us the industrial production coefficients, that is important in one point and not in other points, because of we have in the literature some things like discrete mixture in the stochastic volatility to deal with COVID-19, for example. This is important to you or not?
It's definitely important, and thanks for the question. I think is a very good one, and I agree. I mean, it matters. In principle, one way in which we could think about this issue is having a TD student here instead of a Gaussian for the error term. Now, that's not impossible to do in our setting. It requires some thinking, but at the moment, we don't think about, or at least not carefully as we should. We don't think about outliers. One way to get around it, it would be the TD student here. Now, the best answer that I can give is that in simulation, we look at the short-lived predictors, so predictors that are active for 2 quarters only, and we can capture that type of dynamic reasonably well. Now, the problem is if that significance is because of an outlier rather than for fundamental reasons, we cannot discriminate that. It's not something that we could do at the moment. The effect of outlier or underweighting the effect of outlier in the variable selection, that's not something that we do at the moment. To some extent, if you do a spike and slab, you don't do either. So if you look at even the Giannone Lenza Premiceri paper, and Eddie Berlopez actually has an interesting paper on which is called the illusion of sparsity, that makes exactly that point, whereby if you have outlying signals and if you live in a Gaussian world, your variable selection could be problematic. My gut feeling is that to some extent we suffer a little bit of that issue as well. So your question is very well taken. We don't address it at the moment.
Thanks.
Okay, Daniele, thanks very much for your presentation. Very nice paper. Okay, thanks very much.
Thanks.
Bye-bye.
Thanks a lot for having me.
Thanks, everyone.
Bye, everyone.
Bye-bye.
Bye-bye.